All right, guys, title your notes today, reading graphs. Today's lesson is grueling. It's gonna be, there's a lot of information in here. And so, don't give up. And I want you to remember that the path to enlightenment is through the swamps of confusion. We're going to start off with a little bit of review, and then we're going to jump into how to read a velocity versus time graph. Here we go. A position versus time graph shows us where something is as time goes by. Take out Quizlet 2 to take a look at this. So don't forget our trick that we do. We rotate the paper sideways. We put our paper here. And this is the position in the positive and the negative direction. As we go from 0 to 1 second, we see that the position is moving is positive. As we move from 1 to 2 seconds, we notice that the position is not changing. As we go from 2 to 3 seconds right there, we see that the position is negative, and from 3 to 4, the position is positive. What does the slope on a position versus time graph tell us? The slope on a position versus time graph tells us the velocity. How is velocity different from speed? Well, velocity is a vector. It has magnitude and direction. So the difference is that velocity has direction. Speed does not have direction. It's just how fast you're going in your car. Driving down the street, you do not have to know what direction you're going to know the speed that you are going. A velocity versus time graph shows us the velocity of something, positive or negative, as time goes by. Let's take a look at an AP question from 2000. This is our free response question from an AP test from 2000. Before we try and answer the question, let's just understand the graph. So over here we've got velocity, and on here this axis we have time. We've got positive velocity and negative velocity. This is zero velocity. We're going to use our trick. I'm going to turn our graph sideways, put our paper there. And as we go, as time passes, we want to understand what is happening to the velocity. Again, velocity starts off at 0.8 meters per second. What is happening to it over this time interval? What is happening? What happens to the velocity?
All right, so before we even try to answer this question, let's take a look at our graph here. So I want us to look over here at the y-axis with velocity on it. So notice that positive velocity is moving forward and negative velocity is moving backward. What that means is that everything above the x-axis, all of this stuff up here, and this area, everything above it means that we're moving forward. And then everything below the x-axis down here in the red, this is when we're moving backward. So essentially, I want to talk through what this would look like, that I'm actually going to demonstrate it. So we start here, and we're going 0.8 meters per second, and we're moving forward. Our velocity is decreasing, but we're moving forward. Okay, then at this point, when the velocity is 0, this means we are still. Okay, so right here at 4 seconds, and then over here at 18 seconds, this is when we're actually standing still. So again, we are moving forward, but our velocity is decreasing. We're slowing down a little bit. Okay, but we're moving forward in the positive direction. Then we've come to a stop. And our velocity is actually going to increase, because notice how on the side the numbers are increasing. Our velocity, we're speeding up again, but this time we're moving backward. I'm going to go ahead and demonstrate what this looks like to the 9-second mark. So I'm going to go ahead and show you what this looks like. Okay. What this looks like.
Moving forward, my velocity is decreasing. I stop. Moving backward, my velocity is increasing. On a velocity versus time graph, how would you find the area between the line and the zero velocity axis? The line being this line right here, and the zero velocity axis being this line right here. So we want to find the area of this. So how do we find the area of a triangle? Area equals 1/2 base times height. All right, we can do this. So 1/2 times base. Now this is time, so the units will be second. 1, 2, 3, 4 seconds. And the height, which is going to be meters per second. We know the height is 0.8 meters per second. Let me go ahead and plug that into my calculator here. Times 4 times 0.8. Okay. And before I even write the number down, let's take a look at the units. So area, we know we're going to want to have some sort of unit of measurement that is like probably distance or something. So we want to cancel out our s's because seconds are the same on the top and the bottom, and we are left with meters. This makes sense for our unit for area. And the number that I got that I plugged in the calculator was 1.6. So my area between this line and my x-axis is 1.6 meters. So what would that area represent? Well, hint, let's take a look at our meters. So we've got meters here. What do we know has units of meters when we're thinking about those kinematic equations? Well, we know that displacement has units of meters. So the area under a velocity versus time graph is displacement. So what is the question that we are trying to answer here? Letter C says, determine the horizontal position, x, of the cart at t equals 9 seconds if the cart is located at x equals 2 at t equals 0 seconds. All right, so we talked about how the area under the curve is the displacement. So the area under this curve right here is the displacement. Now think back to when I did my demonstration when I was walking. This right here is positive direction. So the velocity, everything above the x-axis over here, this is all positive direction. So I was walking forward in that video. Everything down here, I'll put a little positive here for you guys. Everything down here, well everything, but we're looking at this spot right here. This is, if you remember me, I walked forward first in the positive direction. And then I slowed down, I started walking backward. This is the negative direction, okay? Now, we already have the area under the curve here. We already have the displacement for this first segment right here. We said it was 1.6 meters. So this right here represents 1.6 meters. Now we need to figure out what the area under the curve, in this blue box is, because this will be the displacement here. So I'm gonna go ahead, we'll say area equals 1/2 base times height. So area is 1/2, my base here, so this is 1, 2, 3, 4 seconds, and we want when time goes to 9 seconds. So 5, 6, 7, 8, 9, that's right here. Okay, so this is gonna be 1, 2, 3, 4, 5 seconds. That's my base. Now the height, I'm gonna go from here all the way down to here. That gives me -1.0 seconds.
Meters per second.
Oh, yeah, meters per second. Meters per second, thanks. Okay. All right, so I plug this into my calculator. Let me just plug it in real quick. So I get, cap down. You get 0.5 times 5 times -1, and I get -2.5. And my units are meters. Get that cap. All right, so that means that the area under in this triangle is -2.5 meters. which means the displacement during this time going this velocity is negative 2.5 meters. That negative again just means that we're going in the negative direction. So back to our question. So the question wants to know the horizontal position. So where are we going to be at? What is our position going to be, position X of the cart, after 9 seconds, if at this starting point, t equals 0 seconds, we're starting at 2.0 meters. Go ahead and explain this for you guys. I'm going to give you a visual for it to help you answer the question. So if we start here at 2 meters, we're walking this way 1.6 meters. 2 plus 1.6 is 3.6. Okay, so we've walked this way 1.6 meters, and then we've slowed down, and then now we're walking the other direction 2.5 meters. So let's go something like this. Okay, your job is to figure out, after you've walked this way this much and that way that much, what position are you at? What does the slope on a velocity versus time graph tell us? Let's check it out. So we know that the definition of acceleration is the change in velocity over the change in time. And when we talk about the change in velocity, we're talking about v final minus v initial over the time interval. Let's take a look at our free response question. Let's take a look at this first segment here, from 0 seconds to 9 seconds. So if I was going to calculate the acceleration, because again, the slope on a velocity versus time graph is the acceleration. If I want to calculate the acceleration, I could look at my velocity final, which is going to be -1 meters per second, subtracted from my initial, which is going to be 0.8 meters per second. And then I divide that by the time, and I know I'm going from 0 to 9 seconds, so it's going to be 9 seconds. Okay, so I'm going to go ahead and calculate this. So it was negative, right? Yeah. Negative, turn the calculator on. -1 minus 0.8, and then I divide it by 9 seconds, and I get negative 0.2. And then let's take a look at my units here. So how do I find the units for this? So our units on the top are meters per second divided by second over 1, okay? So we can flip that because we want to do the opposite of what we're doing here. So over here it'll be 1 over s, cancel that out. And when you multiply this across, you get meters per second squared. Those are our units over here, meters per second squared. So you want to remember that anytime you divide fractions, you just flip it over and multiply it on the top. That's a good idea. So now what's next? We've done the first part of letter D with you guys. Your job is to finish the rest. I'll read the question for you one more time. It says, on the axis below, they give you a graph right here. Sketch the acceleration, A, versus time t for the motion of the cart from 0 to 25 seconds. So from 0 to 25 seconds, you're going to use information on the velocity versus time graph to calculate what the acceleration is during each of these segments. And you're going to sketch a graph using the acceleration that you calculate. So how could we take information from the velocity versus time graph that we've been working on and use it to plot a position versus time graph? So in order to figure out how to do this, we need to think about what variables we have so far. So let's see. So on our velocity versus time graph, we have the slope of the line, which is the acceleration. So we've got the acceleration. We have the velocity, and we also have the time. So let's come and take a look over here. So we have the acceleration, velocities, and the time. But what we don't have is the displacement.
And that's what we're looking for.
And that is what we're looking for. So if we take a look at our equations, we can pretty much use any one of the equations except for this one because it's not going to help us solve for displacement. So which one do we use? If you take a look at the math that you'll have to do to get d by itself, this is going to be way more work than we want to do. Same thing with this one. This square in here is going to make things challenging. So I think the easiest one is going to be this one, to use this one. So we are going to use this equation to solve for displacement. So let's go ahead and take a look at our equations. I kind of laid them out here for you. Again, we are using this equation. However, if you think back to our equation for displacement, the equation is x final minus x initial. What we want to do is find x final. So if we want to get x final by itself, we have to get rid of this. Right now we have subtraction. If we want to get rid of it, we have to do the opposite of subtraction. So we're going to add x initial over here on this side. It's going to give us an equation that looks like this. So x final equals 1/2 velocity final plus velocity initial times time plus initial position. Okay, so the last piece of information I want to give you guys is that our initial position is going to start off at 2 meters at time equals 0. So we want to know what is x for every second from 0 to 25.
Ms. Moore, that's going to be a lot of work.
This is a long question. It's a hard question. It's a grueling question. We're going to break it down into chunks, 5 different chunks. So we're going to focus on this chunk first, this chunk second, third, fourth, and fifth. Let's start here. So we have all of these variables. Let's go ahead and label what we have on here. So we know that right here we have our velocity initial, which is always going to equal, for this segment, 0.8 meters per second. Our final velocity at time equals 1, okay, is going to be right here. So velocity final at time equals 1 second is going to be right there. Let's see, what else do we have up here? That's it. Okay, so let's go ahead and go to second 2. Okay, so right here we have our final velocity at t equals 2 seconds. 1, 2, at 3 seconds. Okay, right there. Velocity final t equals 4 seconds. And then let's see right here. Our velocity final at t equals 5 seconds.
Etc.
Etc. Keep going on, okay? All right, so I'm gonna do the first one with you guys. So you can see how I'm labeling this. So I'm gonna go ahead and plug this in. So velocity final equals 1/2. So I'm gonna say, actually, I'm gonna pause for a second. I'm gonna make this a little bit easier. The only 2 variables that are gonna be changing this entire time are our final velocity and our time. So essentially, I'm gonna use this equation for this entire time span from 0 to 9 seconds. I'm gonna use this equation that I write. My final velocity is gonna be what I plug in, plus my initial velocity, which is gonna be 0.8 meters per second. My time is what I'm gonna plug in. And my initial position, if you look at the board again real quick here, we said that our initial position is always gonna be 2 meters. So we're starting right here, 2 meters. So it's always gonna be plus 2 meters here. So this is gonna be the equation that we use the entire time. The only difference is our final velocity and our time are gonna be different. We're gonna plug in different things. So for this first second, at t equals 1, we put a 1 right here. And for our final velocity, we put 0.6. Okay, 1/2. And then we're gonna say final velocity, 0.6 meters per second plus 0.8 meters per second, I'm out of space here, times 1 second plus 2 meters. I'm gonna go and plug that in. Okay, so we'll go, oops, 0.5 times 0.6 plus 0.8 times 1 plus 2. Okay. And I get 2.7. I know I'm talking about meters here because we're talking about position. So I'm gonna put meters right there. So we've just gotten this answer. We want to transfer this answer to our t-chart. We know at time equals 0 seconds, position was 2 meters. It gave us that in the question. And then after 1 second, now we've gone now we are at 2.7 meters. Okay. So now we do the same exact thing, but we need to go at time equals 2 seconds. So I'm just gonna change these two right here. So at time equals 2 seconds, I'm gonna put 2 seconds right here. And then for the velocity at 2 seconds, this is 2 seconds right here, it was 0.4 meters per second. So, oh, right here is the guy. So if I plug this in, okay, it was 2 seconds there. Oops, I'm going to start over here, 0.4, 0.4 plus 0.8 times 2 plus 2. Boom. And this time I get 3.2 meters. So I'm going to take that answer, put it up here. And you're going to do the same thing all the way through t equals 9 seconds. So now you guys do the rest of these. I'm gonna hop down to where t equals 9 seconds, so right here. And so I'm gonna go ahead and plug that in. So we'll go 9 right here, 9 seconds. And at 9 seconds, our velocity is -1 meter per second. Let's go ahead and plug that in. So 5 times -1 plus 0.8 times 9 plus 2. Familiar answer. Okay, so we get 1.1 meters is our position at t equals 9, right here. And this should be familiar. When doing letter C, we were trying to figure out the position when t equals 9. And we got 1.1 meters, which is the same thing that we got doing this. So there's more than one way to answer these questions. There's more than one way to tackle a problem, and you can see that here. So I'm gonna go and take this number and I'm gonna put this right here. All right, so since we have a new segment, we are gonna need to create a new equation. Our new initial position is going to be what we got for the last answer at t equals 9, so 1.1 meters right there. And so let me go ahead and change that up here, 1.1, that's our new initial position. And our new initial velocity is not 0.8 anymore. Instead, it's gonna be whatever is right here, so -1 meter per second. So I'm gonna erase this guy, -1 meter per second. I'm gonna make that adjustment here as well. Meter per second. Now, every single time we're gonna be changing these numbers again still. So let me go ahead and start from scratch here. I come down here, so even though this is at t equals 10, at 10 seconds, we're actually gonna call this 1 second still when we plug this into our equation. So at this spot right here, this is going to be our final velocity at t equals 1 second. And then right here, this will be our final velocity at t equals 2. And then this will be our final velocity at t equals 3. Let's start right here. We're gonna say our final velocity is gonna be -0.8. Okay, -0.8. And our time is, again, we're not going to use 10 seconds, we're going to use 1 second. Okay, so 1 second right there.
Why are you using 1 second, Mrs. Moore?
I'm using 1 second because we look at this as one time segment from 1 to 9, and then we look at this as a separate time segment. And we're going to be using 1 second, 2 second, 3 second.
Oh, that makes sense to me.
So okay, back over here. I'm going to go ahead and plug this into my calculator. So 0.5 times negative 0.8 plus negative 1 times 1 plus 1.1, and I get 0.2. Put this down. So 0.2 meters. Now, what do we do with this? We come down here, we go ahead and put it in our chart. Okay, and then what you guys are going to do is you're going to keep on going, and again, the only numbers that you are going to change are the velocity right here and the time right here. So in order to do this next time interval right here, I need to figure out what the final velocity was in this spot right here at t equals 3. So I'm going to plug it over here. So time equals 3. My final velocity is negative 0.4. Calculator. 0.5. 0.4 plus 1 times 3. 1.1. Okay, I got negative 1. Okay, so negative 1 for our position, and then I'm going to go ahead and write that down here, negative 1 for our position. Okay, so now again we are doing a new line segment right here, so we are going to make a couple notes here. So our initial position is going to be negative 1 here.
Meters.
Meters, thanks. And let's talk about our velocity final. And again, this is going to be, we need to move this to right here. Okay, our velocity final again at time equals 1, because again, it's a new segment. So although this is at 11, 12, 13 seconds, we don't care about that. What we want is to know is that it's at the 1 second mark when we're doing our actual calculation. So let's go ahead and plug this in. Oh, that's another thing to remember. So let's take a look at this line segment right here. You'll notice that it's a horizontal line, and that means that if you take a look over here, our velocity is negative 0.4 meters per second this entire time. What does that mean for our equation? So that means that our initial velocity is always going to be negative 0.4. And our final velocity is also actually always going to be negative 0.4 during this time. So the other thing that's changing is going to be, we have to fix this. We said that our new original position is negative 1 meters. And the only thing that's changing is going to be our time. And again, like I said previously, we're looking at a new segment. So this is going to be t equals 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds. You guys can take it from here. I want you guys to finish up this segment and then do this one and this one. So we went over a lot of stuff today. Just a real quick recap. Let's talk about what information we can get from a position versus time graph. Well, we can get where something is as time goes by, and we can also get the slope. And the slope of a position versus time graph is the velocity. The other graph that we looked at was a velocity versus time graph. So, what information can we get from that? Well, again, we can learn how fast something is going and in what direction it's going, either forward or backward. And we can also, again, calculate the slope of the line to get the acceleration.